So Mina from SynSense.
Yes, right.
Okay. That's perfect. So we are going to leave the drone space, but we're gonna keep the focus on neuromorphic solutions.
Exactly.
So welcome.
Yes. Hi, everybody, and thanks for Federico, with a perfect introduction prepared for my talk. In fact, this was supposed to be presented with my colleague, Nogai Küpeleoğlu, who unfortunately couldn't join. He had to cancel his trip due to some last-minute complications. So I'm presenting this on behalf of him. The work that I'm presenting is about a low-power, low-latency multi-object tracking algorithm and tracking and classification algorithm using a fully event-driven neuromorphic pipeline. So this is actually a good continuation to the previous talk. I will not talk about drones, but this algorithm has great potential of being deployed on drones. A short introduction again about our company. Since we were founded in 2017 in Zurich, we have offices in China, in Chengdu, Shanghai, and Shenzhen, and we were basically a spin-off of a research lab in ETH. We work on we build low power and low latency applications on various type of sensors, audio, IMU, biosignals, and cameras. Yeah, we have a hardware family, and here to answer the question that we had about if an event-driven camera can be integrated in a neuromorphic chip, yes, we have it here in a spec. So our main chip is Dynapse CNN, which is contains a scalable SNN cores, and spec system on chip is that scalable SNN cores integrated with a camera. DVS camera, and we have built applications like a small, smart presence detection, gesture recognition, and so on with this chip. And the second family of chips are Xylo, the ones that probably, if you have been on my talk yesterday in the tutorial, I presented it. It's a digital SNN processor, digital spiking processor for spiking neural networks. It's ultra low power, and it is designed for low dimensional signals like audio and IMU and so on. So the problem that we are focusing on it today is a well-known problem of object localization, which contains identification and localization. There are many methods, both in classical computer vision, and also in recent years, many advanced methods in deep learning for that. Well-known ones were region-based CNNs, RCNNs, which were at the beginning very computationally intensive. Then there were different improved versions of that, fast RCNN and faster RCNN, as far as I could follow. And then there was YOLO that I'm sure all of you know, and then different versions of YOLO. And the tiniest YOLO still has few million neurons. So the solution that we are proposing here is a fully event-driven neuromorphic solution with neuromorphic cameras and neuromorphic processors, and it is low power, low latency. So yeah, again, a quick reminder of what is the issue with conventional cameras and what dynamic vision sensors and event-based cameras bring to the table is that conventional cameras suffer from motion blur, so they basically miss what's happening between two frames. So that's why sometimes we see this kind of blur on that. And then they are also insensitive to the information content of the scene. So they just keep sending information with a fixed frame rate, even if there is interesting things happening in the scene or not. So they are not really, they are not sensitive to the local, like spatiotemporal content of the scene. And dynamic vision sensors or event-based cameras, on the contrary, they are, as Federico well presented, they are sensitive to the change in luminosity And whenever there is a significant change in the luminosity, they produce an event at each pixel is completely independent, so we can have a very few percentage of pixels in the scene spiking and sending events, and the others, which they don't receive any significant change or interesting information, they remain silent, and that's how we get rid of redundant information processing. And this can be, basically, this asynchronous spike generation at the camera level can be with the resolution of microsecond. And yeah, with this picture, I hope you will see what I mean. Okay, this is supposed to, sorry. This is supposed to, yeah. So yeah, in this picture you see how basically the frame-based image lags behind what we can get with the event-based camera for the case of tennis player, which basically includes very high speed movements. And also in the picture in the bottom you see that basically event-based cameras, they are sensitive only to motion. So if there is no motion in the scene, they wouldn't communicate any information with them. It's like, yeah, sensitive to motion. Like a fast review of what is in the state of the art, there has been a state of the art for object recognition. As I mentioned before, there has been region-based convolutional neural networks for many years and different versions of that. Basically, there was a pre-processing stage to select those regions, to recognize those regions and pass each of them separately in a serial manner most of the time to a convolutional neural network, which was extremely computationally extensive. And then YOLO came along with which was doing it in one shot in a grid-based recognition, classification, and regression task. Still, even YOLO, even the tiniest YOLO, has so many parameters, so many memory requirements, and so on. And it's not always easy and convenient to use them as a object localization algorithm. What we propose instead is using spiking neural networks, which are they have sparse and binary activations, and they basically propagate change instead of any data that they receive, completely compatible with the DVS cameras. So if there is no change, they silent. So chaining DVS cameras with a spiking neural network makes perfect sense. And so in this algorithm, we have separated regression and classification task for object localization. And this with this serialization, basically we reduce the dimensionality and it becomes easier. And also this is compatible with how it is done in the brain. In the brain, we have also where and what pathways, one focused on what we see and the other one focused on where we see it, and they both are independent and they complement each other. Finally, let's have a demonstration of how the algorithm works. So the tracking part is that, so what you see in the picture is output of an event-based camera. It is different clusters capture, basically cover the whole scene and basically capture what's happening in the scene. We have oval-shaped clusters here, and whenever there is a new event received, it is first algorithm tries to assign that new event to one of the clusters. And if there is no appropriate cluster for that, generates a new cluster for that event, and so on. And these clusters shrink and grow in size and so on. That's how we basically, a number of clusters is generated from the information in the scene. And these clusters, the convolutional neural network is trained with the information from these clusters, a very simple convolutional neural network. This is for the classification part, and we in this case, we train the convolutional neural network, and then we convert it to SNN with rate coding. And we have deployed it on DynapCNN, our processor. And by the way, Synapse is our library to develop applications for this chip, DynapCNN. It's open source. And in few line of code, we can develop this on Synapse. And yeah, again, a review of the whole pipeline. At the beginning, so we get the information from DVS sensor, the content gets filtered, clusters are generated with the clustering algorithm. Then different clusters are passed to different SNN cores, and each of them is a simple, lightweight spiking neural network which has been trained for classification of those. So what you see in the animation at the right is that the name of, I hope it's visible, the name of objects comes from the SNN, from the classification part, and as you see, they change color sometimes. It means that they change location, and that's the regression part that comes from the cluster. Another interesting experiment that Nogai did is train this network for toy cars. So here, what you see at the left is the full visual field of the DVS camera. Two little toy cars entering to the visual field, and two clusters. They correspond to two clusters, and they pass. Each of them is given to a SNN core, and then what you see at the rightmost column is what the network predicts for the type of the car. Yeah. And yeah, another demo of the same scene here. Nogai basically leaves the cars on a ramp. It's a very quick movement, half a second or so, and network is able to very quickly recognize the type of car and the location. Let's see it once more, maybe. We have done some latency measurements. It's extremely fast. In average, it takes about 5 milliseconds to classify the object. So it's the output of what you see at left is the output from readout neurons of SNN for these two cars. And in about 5 milliseconds, the network was confident enough about the class that it predicts. And at the right, you see the magnified versions of that red highlighted window for 5 milliseconds. So as soon as having enough events, the network quickly decides and predicts. And also about, let me tell you about some accuracy tests. So here in the figure, what you see is accuracy of the network on the whole test set. In about 6 milliseconds, the network already reached to its top accuracy, peak accuracy. And on the full test set results on the original convolutional neural network is about 97. In SNN in simulator is about, again, 97. And the accuracy on the chip is 95.8. So we have like less than 2% of drop between the original trained CNN and the deployed version on the chip. And this figure is about the estimated power. The power is estimated per object, per cluster information, and then the number of synaptic operations in that cluster here has been shown for a duration of 5 seconds. And based on the number of synaptic operations and the some value of picojoule for each energy of each synaptic operation, power estimation, power is basically estimated for 5 milliseconds. So what you see is that the object is entering to the cluster, then the SNN gets the load, the computational load of the SNN increases, reaches to its maximum, and then it decreases and then eventually goes silent. And in average, it's about 1.5 milliwatt of power consumption, and the peak on the test data set has been 9 milliwatt. To summarize, serializing and separating localization from classification, regression from classification is highly beneficial. It reduces the computational cost, and also it reduces memory requirement because our input space is low dimensional, and we are able to track very fastly moving object with dynamic, not only with dynamic vision sensors, but we are also able to process them real time. Yeah, that's all. I thank our colleagues on behalf of Nogai, and if there is any question, I should be able to answer them if they are not very detailed.
Many thanks for the brilliant presentation. So before the question, of course, we need to thank you for that.